we solve the problems of chapter number 9, and you guys know that chapter number 9 is related to the force on current carrying conductors. We do question number 6.1. In question number 6.1, a differential current element having length of 2 into 10 raised to power minus 4 meter carries a current of 8 ampere in the AZ direction. How much force is experienced by this conductor if it is placed in a magnetic field of 2 into 10 raised to power minus 5 AY Tesla? So if you look at the data of question number 6.1, the differential length of the current carrying conductor is given to you guys, which is 2 into 10 raised to power minus 4 meter. The current in the conductor is 8 ampere. This current is in the direction of the unit vector AZ. We know that the differential length vector is always in the direction of the current. So the differential length vector will be in the direction of the unit vector AZ. This is the magnetic flux density, which is 2 into 10 raised to power minus 5 AY Tesla. This current carrying differential element is placed in this magnetic flux density. Definitely force will be experienced by this differential current carrying element, and we need to find out this differential force. So we know that the differential force is equal to IDL cross P. So if we multiply the current by the differential length vector, we get 16 into 10 raised to power minus 4 AZ. And the magnetic flux density is 2 into 10 raised to power minus 5 AY. We simplify this cross product, and this cross product results in the differential force, and the differential force is minus 32 AX nanonewton. This is the differential force which is experienced by this differential current carrying element. We do example number 6.2. In example number 6.2, we have a charge of 2 into 10 raised to power minus 3 coulomb. This charge is moving with a uniform velocity of 3 AZ meter per second in a magnetic flux density of 2AX minus 3AY Tesla. Find the magnetic force experienced by this charge. If we consider an electric field intensity of minus 2AY plus minus 2AX plus 2AY volt per meter, then find the magnitude of the total force on the charge. So in part number 1 of this particular question, the charge of 2 into 10 raised to power minus 3 coulomb is moving with a uniform velocity of 3 AZ meter per second in a magnetic field. Force will be experienced by this charge due to the magnetic field, and we need to find out this force. While in part number 2, this charge is moving in the magnetic as well as electric field. So force will be experienced by this charge due to the magnetic as well as electric field. We need to find out the total force which is experienced by this moving charge. So let us do the first part of the question. In the first part of the question, we need to find out the force on the moving charge due to the magnetic flux density. The force on the charge will be equal to Q into V cross B. So we multiply the charge by the velocity of the charge. So we get 6 into 10 raised to power minus 3 Az cross the magnetic flux density, and the magnetic flux density is 2Ax minus 3Ay. We simplify this cross product. So the simplification of this cross product gives you the force which is experienced by this charge in the given magnetic field, and this force is 18Ax plus 12Ay millinewton. Let us do the second part of this particular question. There are two sources which are exerting force on the moving charge. Number one is the magnetic field, and we have already calculated the force on the charge due to the magnetic field. The second source is the electric field, and let us calculate the force on the charge due to the electric field. We apply the superposition theorem over here. We find out the force on the charge due to the magnetic field in the absence of the electric field, and then we find out the force on the charge due to the electric field in the absence of the magnetic field. So we use this particular equation to find out the force on the moving charge due to the electric field. We multiply the charge by the electric field intensity, and we get the force on the moving charge due to the electric field intensity, which is minus 4Ax plus 4Ay. According to the superposition theorem, we take the vector sum of these two forces, and the vector sum of these two forces results in the total force. So we add these two forces to find out the total force on the moving charge. So the total force on the moving charge is 12Ax plus 16Ay millinewton. We find out the magnitude of this force, and the magnitude of this force is 20 millinewton. We do example number 6.3. In example number 6.3, we have two differential elements. I1 dl1 is 8 into 10 raised to power minus 4 Az ampere meter, and I2 dl2 is minus 8 into 10 raised to power minus 4 Az ampere meter. These two differential current elements are located at 0, 0, 0 and 0, 2, 0 respectively. Calculate the differential force on the first differential current element and the differential force on the second current element. These two differential current elements are located in the magnetic field of each other. So definitely there will either be a force of attraction or force of repulsion between them. We need to find out the differential force on the first element and the differential force on the second element. So let us find out the force, the differential force on the first differential current element due to the magnetic field of the second differential current element. The force which is experienced by the first differential current element will be equal to I1 dl1 cross db2, where db2 is equal to mu naught by 4 pi into I2 dl2 cross r1 minus r2 by 4 pi r1 minus r2 raised to power 3. So we use this particular equation to find out the differential magnetic flux density. We put the values in this particular equation. We get minus 8 into 10 raised to power minus 11 Az cross minus 2 Ay divided by 8. So the differential magnetic flux density, which is generated by the second differential current element, is minus 2 into 10 raised to power minus 11 AX Tesla. We put the values in this particular equation. So let us put the values in this particular equation. Putting the values in this particular equation, the differential force on the first differential current element will be equal to 8 into 10 raised to power minus 11 Az cross minus 2 into 10 raised to power minus 11 Ax. And the differential force which is experienced by the first differential current element is 16 into 10 raised to power minus 15 Ay Newton. Now we do the second part of this numerical question. The differential force which is experienced by the second differential current element will be equal to I2 dl2 cross db1. We use this particular equation to find out the differential force on the second differential current element. Let us calculate db1. So we calculate db1 with the help of this first equation, and then we put the values in the first equation. We have 8 into 10 raised to power minus 11 Az cross 2Ay divided by 8. So the differential magnetic flux density which is generated by the first differential current element will be equal to minus 2 into 10 raised to power minus 11 Ax Tesla or Weber per square meter. Then we put the values in this particular equation. I2 dl2 is known. db1 has been calculated. So let us put the values in this particular equation. the differential force will be equal to minus 8 into 10 raised to power minus 4 Az cross minus 2 into 10 raised to power minus 11 Ax. So the differential force which is experienced by the second differential current element is 16 into 10 raised to power minus 15 Ay Newton. So this is the differential force which is experienced by the second differential current element due to the magnetic field of the first differential current element. Example number 6.4. Again, we have got two differential current elements. The first differential current element is I1 dl1, which is equal to 2 into 10 raised to power minus 3 Az ampere meter. And the second differential current element is I2 dl2, which is 4 into 10 raised to power minus 3 Az ampere meter. They are located at 220 and 340 respectively. Calculate the differential force on the first current element and the differential force on the second current element. Well, the differential force which is experienced by the first current element will be equal to I1 dl1 cross dB2. We calculate dB2 with the help of this particular equation. dB2 will be equal to mu naught by 4 pi into I2 dl2 cross R minus R2 by R1 minus R2 raised to power 3. So we put the values over here. We have 4 into 10 raised to power minus 10 Az cross minus Ax minus 2 Ay divided by 2.24 raised to power 3. So we simplify dB2 over here. We have 0.356 into 10 raised to power minus 10 Az cross minus Ax minus 2 Ay. And the differential magnetic flux density which is generated by the second differential current element is 0.7 Ax minus 0.356 Ay into 10 raised to power minus 10 Tesla. So we have calculated the differential magnetic flux density dB2. We put the values in the equation, and the differential force which is experienced by the first differential current element is given by this particular equation, which is 0.7 Ax minus 1.42 Ay into 10 raised to power minus 13 Newton. Now we calculate the differential force which is experienced by the second differential current element, and this force will be equal to I2 dl2 cross dB1. We calculate dB1 with the help of this particular equation. We have mu naught by 4 pi I1 dl1 cross R2 minus R1 by R1 minus R2 minus R1 raised to power 3. So let us put the values in this particular equation, and we get 2 into 10 raised to power minus 10 az cross ax plus 2y by 2.24 raised to power 3. We simplify this equation, and the simplification of this equation gives you the differential magnetic flux density, which is generated by the current in the first differential current element. And this differential magnetic flux density is dB1, which is 0.356 AX plus 0.178 AY into 10 raised to power minus 10 Weber per square meter or Tesla. We put the values in the equation for the differential force 1. So we have 4 into 10 raised to power minus 3 Az cross 0.356 AX plus 0.178 AY into 10 raised to power minus 10. We simplify this equation, and the simplification of this equation gives you the differential force which is experienced by the first differential current element, and this differential force is 0.71 AX plus 1.42 AY into 10 raised to power minus 13 Newton. Example number 6.5. Consider a current carrying loop in a uniform magnetic field of 2 into 10 raised to power minus 3 AY Tesla is shown in figure number 11. Find the total force and the total torque on the loop if it carries a current of 4 ampere. So we have a current carrying loop which is shown in this diagram. You see the loop is located in the z is equal to 0 plane. We need to calculate the total force on the loop. In order to calculate the total force on the loop, we will consider this side of the loop, the side L1 of the loop, and we will calculate the total force. We will calculate the force on side L1. We shall calculate the force on side L2. We shall calculate the force on side L3. We shall calculate the force on side L4, and we shall take the vector sum of all these 4 forces. The vector sum of all these 4 forces will give you the total force on the current carrying loop. Well, we consider L1. So the force which is experienced by L1 will be equal to IL1 cross B. We put the values in this particular equation. So F1 will be equal to 16 AX cross 2 into 10 raised to power minus 3 AY If we simplify this equation, F1 comes out to be 32 AZ millinewton. Now we consider L2, the force which is experienced by the side L2 of this current carrying loop will be equal to IL2 cross B. Well, if we multiply L2 by the current, we get 8 AY. So the force on this side of the current carrying loop will be equal to 8 AY cross 2 into 10 raised to power minus 3 AY, as AY cross AY results in 0, so the force on this side will be 0. So the force on this side of the current carrying loop is 0. We consider side L3. The force on side L3 will be equal to IL3 cross B. If we multiply L3 by the current, we get minus 16 AX. And the magnetic flux density is 2 into 10 raised to power minus 3 AY. So the force F3 is minus 32 AZ millinewton. Then we consider L4. So the force on this side will be equal to IL4 cross B. If we multiply L4 by the current, we get minus 8 AY cross the magnetic flux density, which is 2 into 10 raised to power minus 3 AY. We know that AY cross AY results in 0, so the force on this side will be 0. Now we take the vector sum of all these four forces, and the vector sum of all these four forces result in the total force, which is 0 Newton. We calculate the torque on the loop, and we calculate the torque on the loop with the help of this particular equation, IS cross B. We know that S is the area of the loop. If you calculate the area of the loop is 8. The unit vector which is normal to the area is AZ. So the current in the loop is 4 ampere. The area of the loop is 8 AZ. The magnetic flux density is 2 into 10 raised to power minus 3 AY. If we simplify this equation gives you the total torque on the current carrying loop, and the total torque turns out to be 64 AX millinewton meter. We do the last question of chapter number 9, which is question number 6.6. Consider a current carrying loop in the magnetic field of an infinitely long current carrying conductor as shown in figure number 6.12. Find the total force on the loop if it carries a current of 1 ampere. So let us consider the figure for question number 6.6. You see, we have got a current carrying conductor which is extending from minus infinity to plus infinity along z-axis. We consider this particular conductor. The current in this conductor is 5 ampere. and this current is in the direction of the unit vector AZ. We have got a current carrying loop over here, and this current carrying loop is located in the magnetic flux density of, in the magnetic field of this current carrying conductor. So let us calculate the magnetic flux density inside the loop. You see the magnetic flux density is given by B. So we know that the magnetic field intensity, which is caused by an infinitely long current carrying conductor, is equal to I by 2 pi rho into A phi. Definitely the magnetic flux density will be equal to mu naught H. So B will be equal to mu naught into I by 2 pi rho A phi. If we apply the right hand rule, this unit vector A phi comes out to be minus AX. So we have minus mu naught I by 2 pi y AX. Rho in this particular case is equal to Y. So if we put the values over here in this particular equation, the magnetic flux density, which is caused by this infinitely long current carrying conductor inside the current carrying loop, is minus 10 raised to power minus 6 by Y AX. So this is the magnetic flux density. If you guys want to calculate the total force on this current carrying loop, you guys will have to consider side L1, and you guys will have to calculate the force on this side of the loop. Then you guys will have to calculate the force on side L2, then the force on side L3, and then the force on side L4. So let us consider side L1. You see, we consider side L1. If we consider side L1, x is 0 along this side, definitely dx will be 0. Y is 2 along this side, so dy will be 0. Only z is changing from 4 to 0. So we consider side L1, x is 0, so dx will be equal to 0. Y is 2, so dy will be equal to 0. And only z is changing from 0 to 4. As only z is changing, so the differential length vector, will be equal to dz az. Why? Because only z is changing. And we calculate the force on this side with the help of this particular equation. F1, which is the force on side L1, will be equal to I. Then we have the integration of dl cross B. Let us put the values in this particular equation. The current is 1 ampere. dl is dz az. Cross and B is minus 10 raised to power minus 6. Y along this side is 2, so we put the value of y over here, which is 2, cross AX. And you see the only variable on the right hand side of F1 is Z, where Z is changing from 4 to 0. Well, we simplify this integration. The integration of dz is Z. So F1 is minus 0.5 into 10 raised to power minus 6. The integration of dz is z. The limits are 4 and 0, and we know that az cross ax results in ay. So the force on side L1 is 2 into 10 raised to power minus 6 ay Newton. This is the force on side L1. Now we consider side L2. Let us consider the figure number 6.12 and let us consider side L2. You see x is 0 along this side, so dx will be equal to 0. Z is 0 along this side as well, so dz will be equal to 0. Only y is changing from 2 to 4. So we consider side L2, x is 0 along L2, so dx will be equal to 0. Z is 0 along L2, so dz will be equal to 0. Only y is changing from 2 to 4. As only y is changing, so definitely the differential link factor will be equal to dy ay. And we calculate the force on this side with the help of this integration. We have I, then we have the integration of dl cross b. So let us put the values in this particular equation. F2 will be equal to the integration of dy ay cross b, and b is minus 10 raised to power minus 6 by y ax. The only variable on the right hand side of F2 is y, and y is changing from 2 to 4. You see, the integration of dy by y is log of y. And ay cross ax results in minus az. So F2 will be equal to 10 raised to power minus 6 into log of y. The limits for y are 2 and 4 az. So we put the limits on this particular equation, and F2 is equal to 10 raised to power minus 6 into log of 4 by 2 az. If we simplify this particular equation, F2 comes out to be 0.69 into 10 raised to power minus 6 az Newton. This is the force which is experienced by L2. Now let us consider L3. We consider figure number 6.12 and we consider L3. If we focus on L3, you see x is 0, dx will be equal to 0. Y is 4 along L3. Y is not changing, it is constant, which is 4. So definitely dy will be equal to 0. Only z is changing, and z is changing from 0 to 4. So we consider L3 where x is 0, so dx will be equal to 0. Y is constant, so dy will be 0, y is 4. Only z is changing from 0 to 4. As only z is changing, so definitely the differential length vector will be equal to dz az. And we calculate F3 with the help of this particular integration. We have I, the integration of dl cross b. Let us put the values. dl is dz az cross b is minus 10 raised to power minus 6 by y, and you see y is 4. So we have minus 10 raised to power minus 6 by 4 AX. The integration of dz is z and AZ cross AX well results in AY. So the integration of dz is z. We put the values, so we have minus 0.25 into 10 raised to power minus 6 cross z. Definitely we will put the limits in z, and then we have AY. So the force on L3 is minus 1 into 10 raised to power minus 6 AY. You see this force is 1 micronewton. Now we consider side L4 of figure number 6.12. If we consider side L4 of the current carrying loop, x is 0, dx will be equal to 0, z is 4, dz will be 0, and y is changing from 4 to 2. So let us consider L4. We consider L4. You see this is L2. This is an error. Consider L4. If we consider L4, x is 0, so dx will be equal to 0. Z is 4, dz will be equal to 0. And y is changing from 4 to 2. As only y is changing, so the differential length vector will be equal to dy ay. This is the differential length vector. And we know that the force on L4 will be equal to I, and then we have the integration of dl cross b. So we use this integration to find out the force on side L4. The current in the loop is 1 ampere. We don't consider this 1 ampere. dl is dy ay. dl is dy ay. And b cross b is minus 10 raised to power minus 6 by y. Is it? The only variable on the right hand side of F4 is y, and you see y is changing from 4 to 2. So the integration of dy by y is log of y. So we have F4, and this F4 is 10 raised to power minus 6 into log of y. The limits of y are 4 and 2, and ay cross ax results in minus az. So we put the limits in the second equation, and we get F4, which is minus 0.69 into 10 raised to power minus 6 az Newton. We take the vector sum of all these forces. So the vector sum of all these forces will give you the total force on the loop. And the total force on the loop turns out to be 1 into 10 raised to power minus 6 ay Newton. So the total force on the loop is 1 micronewton.